With orbits closer in than Mercury, and a radius similar of Jupiter, hot Jupiters have not only dominated exoplanet detection and analysis over the field's first 2 decades, but have also demonstrated that our solar system is not the stock standard for where planets should be. But how hot can these planets actually become? And what can we learn from observing these planets in detail? Of the Jupiter-sized planets that have been identified, KELT-9b is not only a hot Jupiter, but it's the hottest one on record to date. It has an equilibrium temperature of over 4,000 degrees Kelvin, rivaling the surface temperature of K-stars, and therefore earning the title of ultra-hot Jupiter. Being first identified in 2017, KELT-9b has since been observed through multiple primary and secondary transit observations, which have used both low and high-resolution spectroscopy techniques. These observations have resulted in multiple atmosphere composition discoveries. In this study, we analysed archival data of KELT-9b, which was observed using TRES, a high-resolution spectrograph mounted on the 1.5 meter reflector at the Fred Lawrence Whipple Observatory situated in Arizona, USA. The data consisted of a primary transit observed in 2014 and 2015, enabling us to search for variations over time in the atmosphere. From our analysis, we were able to confirm previous detections of iron 1, iron 2, magnesium 1, and H-alpha. KELT-9b is the first exoplanet to have iron detected in its atomic state, reaffirming just how hot the atmosphere must be in order to maintain it. Magnesium 1 has also been proposed as an atmosphere coolant due to its chemical nature, with the potential to indicate evaporation. When using our spectral observations to generate a light curve from our H-alpha detection, we uncover an unusual W shape for both transits, a trajectory that deviates from the typical U shape that astronomers have come to expect for transiting events. We explain this through a geometrical model that assumes the atmosphere of KELT-9b is evaporating away from the planet in the direction towards the observer, with the tail being momentarily obscured by the planet during the middle of the transit. While H-alpha has been associated with atmosphere escape in the past, it's only been identified as a secondary tracer, with Lyman alpha and helium-1 being the only primary tracers accepted in the astronomy community. To maintain an extended H-alpha tail outside the atmosphere of the planet is a challenge, given its excitation chemistry and potential sensitivity to temperature beyond the thermosphere, a region it is commonly found in abundance. Being the hottest Jupiter-sized planet we have found, KELT-9b continues to surprise us with what it takes to be in such close quarters with a host star. Given our successful detections of iron 1, iron 2, magnesium 1, and H-alpha within its atmosphere, we have shown the contributions that a high-resolution spectrograph attached to a meter-class telescope could provide to the astronomical community when it comes to atmosphere characterization of ultra-hot Jupiters. The research from this project was an international collaboration led by Natalia Lawson at the University of Southern Queensland and has been accepted to the Astronomical Journal. It is currently available to read in its preprint format on arXiv for those who are interested in learning about this project in greater detail.